Hello everyone, my name is Evgeny Stemasov and I'm here to present a paper named ShapeFindAR or ShapeFindAR. It is meant to be an exploration of in-situ spatial search in the context of personal fabrication. Let me start with a brief look at what we built to do that. ShapeFindAR is an augmented reality application written for HoloLens 2 connected to a database of 3D printable objects. It supports users in searching for their physical context by allowing them to sketch out the geometry they desire, as seen here, or by extracting labels to use for text search based on their environment. The entire process happens at the future location of the object. First of all, a bit of motivation and reasoning for this approach. This is a very simplified depiction of how we get to a physical artifact in the context of personal fabrication. We design it, fabricate it, and then we can use it. We could also go ahead and open up the fabrication step a bit and replace it with something more general, like acquisition. With our work, we wanted to focus on the first stage, which may be described as design. Now, design may be, for instance, 3D modeling, but we can treat retrieval, remixing, or parameter input as design activities nonetheless. With ShapeFindAR, we explore the search and retrieval aspect. We do so in the context of physical artifacts, ones that we fabricate or buy at some point. In the personal fabrication space, there's a commonly used database or community, which you are probably familiar with, named Thingiverse. We have outsourced design effort, which is a lovely entry point, especially for novices. Let's take a look at an example. We want to have this kind of vase with handles. That's a valid search term. If we have the domain knowledge, we could also enter amphora as a term. Looking at Thingiverse, the first query does not yield fitting results up front. The second one, which requires some domain knowledge, does fare a bit better here. The issues we saw here are that these type of searches require domain knowledge for ideal results. They are also disconnected from their physical context, and they require a conversion of spatial requirements such as sizes or proportions to text. This is even then the case if the user would have a rough understanding of their desired geometry. So how can we support users in formulating queries while they are searching for physical objects? How can we leverage their physical context and environment for that? And how may we determine fitting results based on that? Before we dive in, I'd like to briefly go over some research areas and works that have inspired us to develop ShapeFindAR. First of all, we have lovely works that use different modalities to describe physical artifacts, for instance gestures, voice, or sketches. This was also done for search and retrieval interfaces, which to the end user may look fairly similar. There were also approaches to situate search interfaces within users' contexts, embedding context information for retrieval. There are also works that have leveraged XR or spatial computing to support design and fabrication processes. This enables in-situ design and interaction, which may reference existing features more easily. Lastly, we have an array of tools that aim to make design and fabrication more accessible to end users. We consider approaches that are based on databases to also fit into this category. Alright, let's now talk a bit about the concept and the system themselves. First, the process we are aiming for. We have the user, the physical context they are in, and we want to formulate a query. ShapeFindAR allows users to enter their known search terms, of course. It also allows them to extract them from their surroundings based on machine vision. Users can also sketch out the geometry they may want or trace objects present in their environment. This enables them to formulate spatial search queries. Of course, we can combine these two modalities, which allows us to be fairly ambiguous with our search terms, for instance. We can also iterate and refine our queries, preview them in the context, and lastly fabricate the object and permanently add it to our physical context. The user-facing side of ShapeFindAR was built for the HoloLens 2 using Unity and the MRTK. We can, of course, type in search terms and browse the results. We can also preview them in situ. We can also extract search terms from the context. Based on the frame the user sees, we crop the image and send it off to the Google Cloud Vision API. We then receive a set of suggested labels. We can also sketch out the geometry we may want in 3D, as you can see here, and use that as a query. When we have received our first results, we can use them iteratively to formulate new queries, for instance by adding new sketched features to objects. Now that I've talked about what the users see and can do, a quick overview over the backend implementation. We used MongoDB, Flask, and TryMesh for that. We used MyManufactory and Thingiverse as data sources to populate our own database. It consists of approximately 4,000 objects, which were then post-processed to enable geometry-based queries. Each sketch that the user submits is converted to a voxel representation. It is then compared to fitting candidates found in the database. In the backend, we converted all models in our database to voxelized representations. We do the same for the user sketch, and they are aligned via ICP, similar to the data miming paper, and we calculate a score based on overlap. To accelerate queries, we are also pre-filtering the objects based on the proportions of their bounding boxes. This is a method we settled on, but there are many viable alternatives. Let's take a look at some walkthroughs we did with ShapeFindAR. We might have an Arduino clone lying around. The name would be an ideal query, but it is not written anywhere. Therefore, this demands domain knowledge. So we frame the object and we receive suggested labels to use as text queries. We can then preview results in situ. This depicts the transfer between physical context and a textual query. We can also iterate on queries, refining them with the results we get along the way. Say we have found this bowl, but want to have something more elongated. We sketch onto this result and submit this as a new query. We may then receive results that have comparable proportions. This addresses the iteration part of spatial queries. We may also trace relevant features to formulate spatial queries, for instance this flower pot. We can then submit the sketch as a query along with an abstract term, and of course preview fitting results. This depicts the transfer between physical context and a spatial query. Our work certainly has its limitations and has avenues for further improvement. The processing time of our server is not ideal, and the matching algorithm does not always perform as desired. Our dataset is fairly diverse, but also small, as it is a subset of databases like Thingiverse. For future work, we plan to do user studies to understand how search approaches may change with such a tool, and we'd like to add more modalities to the search, such as 3D scans. To wrap it up, we presented ShapeFindAR, an AR tool enabling in-situ spatial search. Searching and finding is a valid entry point to personal design and fabrication, and it can be made more powerful and lowering effort and easing access to model repositories. In the context of fabricating and acquiring physical artifacts, their future context becomes an indispensable feature to use and rely on. And the vision behind this is to let users express themselves in the modality they are comfortable or proficient with, and let them mix them how they want or depending on the task they face. That's it. Thank you very much for listening. Thank you to all my wonderful collaborators too. For more details, please check out the paper.